Okay, so in this video, we're going to continue with our discussion of linear models, or regression in general. And we're going to be looking at initially some revisiting of multiple variable plots, so 3D plots with a couple of different packages. One of these plots we have seen before in a previous video, and we'll reconstruct it. And then we'll also look at a variation of that plot with Plotly. And then we're also going to look at doing transformations of variables to see if we can improve model fit. And finally, we're going to look at penalized regression. So there's going to be a lot going on in this discussion. So let's go ahead and get started. We're going to start by loading a package. Again, if you've never used this particular package before, you will need to go to Tools and install it, and then it will load properly. And this is another package that we can use for plotting in 3 dimensions. So we're going to compare weight with displacement and MPG. S is a scatter plot type. Now, if you're using a Mac, you're going to need to install the Quartz package because this RGL library will pop up in a new window when you run these. So if you're running into any issues with either of these packages, particularly if you're on a Mac, investigate the Quartz package in terms of being able to load these graphs and have them display correctly. But here we're going to run this. Hopefully I didn't make any typos. And yeah, so here's our new window. And we can see this one is interactive, unlike the package, the Scatter 3D that we looked at in the previous video. This one, like Plotly, is a little bit more interactive, but it doesn't have, we haven't customized it in the way that we did in the example we did for Plotly in the in a prior video. But it does allow us to look at it from different perspectives, which is nice. So it's a little bit interactive. Now, if we wanted to improve the look of our axes, we can by adding in some additional elements. So for instance, we can add in things like labels. Replace the generic label with weight, and YLab, we can replace the generic label with displacement, and ZLab, replace the generic variable, the generic label with MPG. And then, again, the order of these attributes doesn't particularly matter. The syntax for the RGL package is a little bit more similar to the base R graphics. And so we've seen these references to XLab, YLab, etc. in the regular plotting function in base R. And so it is a little bit more similar to things we've seen in other videos compared to the Plotly package, for instance, which is very different than either base R or ggplot. And so again, we've seen our labels replaced. We could also add like a title and things like that. All right. Now, we're going to return to Plotly because there's one other kind of graph, 3-dimensional graph that we can model. That should be a library. So we're going to reload that. Now, in a previous video, we actually looked at this same plot, and so I copied it out of the previous example, but we'll walk through what is going on with the code here. So the first thing to notice is that, and in fact, I'm going to modify some of this so that we can see more of it on the screen a little bit. So the first thing is we're taking our empty cars data set as our example, and we have this AM variable, and we want to convert it to a meaningful factor variable. So we're going to reset the 0 value of our variable equal to automatic, and we're going to reset the 1 value of our variable to manual. And then that will be treated in our data set as a factor variable so that we can use it to colorize our graph as discrete values. And then we're going to construct our plot in Plotly. Now, again, the syntax for Plotly is quite a bit different than the syntax for some of our other plotting packages that we've looked at. So here we specify our data set, and then we specify our X, Y, and Z variables, and we have to put the tilde in front of the variable name. And then we specify the color, and again, we're going to use the automatic and manual variable category as the coloring. And then we specify the colors that we want to use. Here we've used specific colors that are in hex code form. And then when we want to add elements to our plot, we use this piping operator to add elements. So this will add the markers, and then we're going to add one more thing, which is some axis labels. And so if we go ahead and we run all of these, then we'll actually reconstruct a graph that we had about 3 videos ago. So if you're following along in the playlist. Let's reload our data. I think it's affected by our previous analysis. There we go. Start over. And so this was the example plot that we had. Again, it's the same one we had before. And again, we can rotate it as nicely interactive. It puts labels on all of our points. We have our color coding. So we're plotting essentially 4 variables on this graph. The color code is 1 variable. We have 3 dimensions to our graph. And if we wanted, we could add a 5th variable to our graph by adjusting the sizes of the plot, the dots, according to yet another variable. We can also use the in this case we're using a discrete categorical variable to do our coloring, but we can also do one that is continuous. And so let's look at that example. Now, a lot of the syntax and the variables that we're going to be plotting are going to be very similar. So I'm going to copy this entire string and then start tweaking it a little bit. So we're going to plot, again, from the same data set. We're going to plot the same 3 variables, X, Y, and Z. But for the color, we're going to change that. So here, we're going to have the marker equal to list, and then the color is going to be by MPG, which is a continuous variable. And then we're going to have a color scale. And then that's going to be a list. And the color scale we're going to use is going to be starting with a yellow. And continuing to a kind of brownish shade. And then comma. And then we're going to show the scale on the screen on the plot. And then, assuming I haven't messed this up at all, we're going to also add markers. And then our scene, we're going to list our x-axis title to be weight, y to be gross horsepower, 1/4 mile time. And then after here, we're going to add some additional things. The annotations are going to have the following: x equals some number, y equals some number, text equals miles US, gallons, xref is paper, and yref is also paper. And show arrow equals false. So let's hope I didn't make any typos and run this. And so here's our legend, our color scale, from this weird yellowy gray color all the way up to our sort of brownish color. And we can see the scale starts down here and goes up to here. So the main colors are between 15 and 30. And again, we can rotate this graph. We didn't put a title on it yet, but we can see that the dots are color coded by this continuous scale. And so the darker ones are over here and the lighter ones, the grayer ones, are over here. Now, the next thing that we wanted to look at was we want to look at whether our variables that we are using in our model are linearly related to each other or not. So we may want to apply transformations to our variables in order to improve the fit. So we're going to look at, in ggplot, we're going to look at two variables and how they relate to each other. So for example, the displacement variable and the MPG variable. And we can see from this that I would not consider this a terribly linear variable. This looks like, to me, like it has a curve to the graph. If I were to try to draw a curve that falls in between all of the variables, I would get something that looked curved, not something that looks terribly straight. So we can try to improve the linearity by transforming the variables. So some common transformations are things like logs or square roots or other kinds of mathematical operations on the variables. So I'm going to create a new variable in my data set, and it's going to be the log of another variable in my data set. And then I'm going to do my ggplot again, but instead of using the original displacement, I'm going to do the log of that displacement. Now that does look more like a straight line, not maybe 100% straight line, but this looks more straight than it was. Again, you can experiment with different kinds of transformations to see if you can get the data. You could try reciprocals or other kinds of transformations to see if you can improve that linearity of the relationship. And then we can calculate the correlation between the original variable in MPG and the log version of the variable in MPG to see which one is better. I remember standard Pearson correlation is measuring that linear relationship. And so if in fact the log did improve the correlation, then it improved the linearity. Now, other kinds of correlation don't require linearity, only increasing and decreasing. So here in the untransformed variable, we had a correlation of negative 0.84. But if we do the log, we actually get that improved to negative 0.9. So it's closer to 1. So that is an improvement. Again, you can try other transformations and experiment with this and see if you can get other kinds of improvements when you're looking at nonlinear variables, because the results will differ by the kind of transformations that you use. Now, we can also apply these transformations before we apply our model and then create our models with the transformed variables, or we can apply them directly inside our models. So we're going to look at some examples of doing it either way. So we're going to create one model. I'm going to use the GLM function here. I'm going to model MPG by the original displacement variable to start with. And then we're going to summarize it. So these coefficients look good. We're getting good fit. All right, so then let's try applying the log process directly inside the model. So our second model will apply the log here. Our p-values went down even from there. And then the alternative is we applied the log externally, and we can see what that does. And in fact, these last two models are exactly identical to each other. If you apply it first, and then you can run the model on the transformed variable, or inside the GLM, you can apply the model, the transformation directly inside your model. And you'll get the same result in either case. Now, if you want to include an interaction term in your model, then you can do that basically the same way that we did with our ANOVA models. So we would use the GLM again, and our formula would be MPG modeled by, and here we're going to include the interaction between displacement and weight. So this indicates we should use displacement and weight as main effect terms and as interaction terms. So by specifying the interaction, we're also specifying the individual separate variable variables be included. And if we summarize this, again, here's our interaction, and we see that all the coefficients are statistically significant, including the interaction. Now, another way to specify this is to specify the individual terms plus the interaction. Now, you may want to do this, for instance, if you don't necessarily want all the possible interactions in your model. Maybe you have like 5 main effect terms, but you only want to include one individual interaction. Then you would want to specify them in a slightly different way. And so in this case, this model has two variables and the interaction, and so the outcome is exactly identical to the previous case. Again, it's just that when you have more variables, if you specify them this way, it'll look at all of the possible interactions, and maybe you don't want all of the possible interactions. Maybe you just want one in particular. Now, we can also include polynomial type terms in our models. Now, this does create some issues with some of the model specifications if you don't do the transformations and then add them to your data set. So let's look at what we have to do to include polynomial terms. So we're going to do MPG modeled by, if we use the gear variable, and I want to use the gear squared variable, I actually have to specify it with this I function. I do the square inside of it, and then the I goes on the outside. It's like a function specification. I can't just do like I could with the log. I couldn't just apply the squaring operation. Data equals empty cars. And then summary. And so this is essentially the gear variable and the gear squared variable. Now, I can also include both interactions and squared terms. So to do that, so I would have, if I want to do the displacement and gear interactions, then I can specify I can specify the squared interactions like that, but then the individual variables I would have to specify separately with this I function. And let's look at the coefficients in our output. So this notation is actually not going to produce gear squared interacting with displacement squared. What it does, it's including the displacement, it's including the gear separately, it's including the square of gear, the square of displacement, and the interactions. And we can see that some of these interactions are not statistically significant. Some of them are marginal. There's probably too many variables going on here, or these two variables are too closely related to each other. So you can do this in order to try to get all of the possible combinations, but it's better probably to just start with a smaller model. Most interaction terms are not going to survive in a lot of models. squared terms will only be statistically significant if the data is strongly nonlinear. And so, again, you may want to experiment with some of these different combinations, but don't be surprised if you try them and you find out that, like here, in this case, the displacement squared is the only one that is statistically significant right now at the 0.05 level. And basically, a lot of these other things just need to come out of the model. And again, you could do backward selection, and you could start by eliminating some of these. For instance, eliminating the interaction term and then seeing where it goes from there. So doing transformations of variables is useful. Now, the issue, of course, is that when you transform variables, you're also transforming the errors. And so it is certainly possible that when you do a transformation of variables, you may create problems in your residuals that didn't exist before, or you may use transformations of variables in order to eliminate problems in your residuals that did exist. So, for instance, if you have non-constant variance, doing a transformation of your variables would also transform those errors, and so maybe you can normalize them or make the variance more like a constant. Now, the last thing that we're going to look at is penalized regression, specifically ridge regression or lasso regression. And for that, again, we're going to need another package, GLMnet. And again, if you haven't run this before, install it under Tools first. And then now, in order to run the penalized regression, we need to transform our variables into a matrix. And we're essentially transforming all of the variables except the first column. And that first column, if I remember correctly, was the MPG column. And then Y is our outcome variable, the one that we're trying to model, and that is the MPG. Now, when they do these penalized regression, we can also do cross-validation in order to try to find the value of the penalized parameter, the lambda, that does the best job. And so we're going to run a cross-validation analysis in order to get that best lambda. So X was the matrix of independent variables. Y is our outcome variable. And this alpha value is actually going to specify the kind of regression, penalized regression that we're doing. So if we set this parameter to 1, we get lasso regression. If we set it to 0, we get ridge regression. And if we set it to a value in between 0 and 1, we actually get elastic net regression, which is a combination of these different penalties from ridge and lasso. So here we're just going to do the ridge regression to start with. And then from this analysis, we're going to extract the minimum lambda. So that's our minimum lambda. And now we're going to construct a model using GLMnet, X, Y, alpha equals 0, lambda equals the value that we just found, lambda min. And then we can get the coefficients of the resulting model. Now, for these penalized regression, they don't necessarily, like for ridge regression, they don't necessarily like backward selection or some of those other selection methods, they don't necessarily drop the variables from the model, all they're going to do is they're going to take all the coefficients and try to adjust the value of the coefficients in order to reduce that penalty so that the ones that are not contributing as much to reducing the residual sum of squares error is going to be minimized. So they'll make those coefficients smaller, whereas the ones that are actually doing a better job of contributing to the model will then be preserved at larger values. But by driving some of the coefficients smaller, you maintain them in the model, but they don't affect the overfitting quite as much. Now, in some of the models, like LASSO, then they're actually going to drive some of the coefficients potentially all the way to 0. And so we're going to run a similar model to look at the LASSO. We're going to change alpha to 1, and then we'll call this another value. We'll plug that in there. And so again, we're going to rerun our cross-validation to find our smallest lambda, or the best fit lambda, but now for lasso regression instead of ridge regression. And then we will rerun our model and extract our coefficients under that smallest lambda. And when you see the dots in this list, this is essentially saying we've eliminated them from the model. They're not doing any good at all. And so instead of just driving them, as we saw in the previous case, to be small coefficients, you can see some of these are very small indeed. In the case of LASSO, they're actually just pushing them out of the model completely. So instead of having just a small linear coefficient for displacement, we actually have a 0 coefficient for displacement. Log displacement does a better job of modeling the data, and so it is preserved at a larger value. So this lasso regression is actually something that you can use in some cases as a model selection tool. Which variables do you want to include? You can run it through LASSO, figure out which variables it wanted you to preserve, and then go back and then reconstruct your model using a traditional GLM or linear model function in order to just preserve those individual variables. And of course, as I mentioned, if you do anything in between 0 and 1, then you'll get what's called elastic net. And so we'll just run that example very quickly. Now you can pick any value between 0 and 1, just as an experiment. I'm going to pick 0.5. Now, the idea behind elastic net is that it's going to have some of the advantages and a sort of combination of effects midway between ridge and lasso. So we can see that the lasso component did in fact drop 2 of the variables from the model entirely, but it wasn't able to drop as many of the coefficients as we had in the pure lasso model. We do still have more variables included, but you can see that the ones that are having the least effect, the ones that were the lasso alone dropped entirely, they are still in the model, but they have very small coefficients.